This talk is about a new implementation of miniKanren and a new implementation strategy for DSLs in general that sort of escapes this usual catch-22 that we're stuck in when we implement a DSL. So we can either use one of sort of these two implementation strategies. We can use a shallow embedding or conventional macros, which are sort of the compile time equivalent of a shallow embedding. And if we use that strategy, then it's really easy to get an extensible DSL that users can add to. And it's really easy for users of the DSL to make it interact with the host language. So in the miniKanren context, implementations like core logic, faster miniKanren, oKanren, these are all shallow embeddings. And they have these advantages, right? But then people like Kate want to implement miniKanrens that have clever optimizations, like we want to implement partial deduction or do some sort of static analysis that lets us have a fair conjunction operation. And if we want to implement those kind of features, then the shallow embedding approach sort of doesn't work, and we have to use a totally different implementation strategy, a deep embedding or external implementation, maybe implemented with a language workbench. But with that strategy, we can get optimizing compilation or a custom static semantics. So that's sort of the trade-off that usually we face. So that's what we're trying to fix. So we have a new approach where we get sort of all four of these things at the same time. And the way we do it is with a new kind of macro system. In particular, implementation of that macro system in Racket is called syntax-spec. And it combines Racket's conventional hygienic macros with specifications of languages with language workbench style meta-languages, and some ideas from multi-language semantics about how to sort of create the connection between the DSL and the host language. So what should the foreign interface between Racket and miniKanren look like? So that's where we're taking our cues from multi-language semantics. And using this approach, we have, so this is where Mitch and Jason came in. They helped me create a new implementation of miniKanren that sort of takes advantage of this feature and implements some interesting extensions and optimizations in one system. And so that's what we'll be sort of looking at how we do today. So I just want to sort of preview some of the sort of advantages that we're going to get out of being able to combine all of these three things together. We'll sort of see these all in demos of them, but just to fill your mind ahead of time. So one part is that by having both extensions and optimizing compilation, we're going to be able to sort of write simpler extensions but still get decent performance because the extension, sort of the output of an extension is going to get optimized. We're going to be able to write extensions that take advantage of host language code, things that we couldn't do in miniKanren alone. And we are going to be able to have an optimizing compiler that's sort of sound in the sense that you can't observe the optimizations that it makes, even though there's some interaction with host language code. So I'm going to show you all of this via a demo. And since it's a demo and I don't want people to get lost, if you, during the demo, have a question that you get lost, you have a question that would help clarify something and keep you following along, feel free to ask. Other kind of questions we should probably keep to the end, though. All right. So I think probably most people in this room know this program, appending a list in miniKanren. If you don't, I'm sorry, but this talk is gonna lose you desperately, I think. But just in case. So we have relation definitions. This is the relation that takes two lists and relates it to a third list, which is the result of appending them. It's sort of a recursive relation. The base case says, well, if the first list is the empty list, then the result of appending them is just the second list, right? And the recursive case pulls apart both the first list and the result where we append it. That's L1 and L3, pulls those both apart and says that the first element of the first list is going to be the first element of the result. And then the rest of the list we're going to handle via sort of a recursive call. So from a logical perspective, we have relations, we have logical disjunction with Condi, we have equality constraints, we have existential variable binding, and that's sort of all that shows up. So in order to implement this using our approach, what we're actually going to start by implementing is sort of a smaller core language. So one of the sort of essential ideas that we're going to follow is that the way we're going to get extensibility is it's going to work in sort of the same way that extensibility for a general purpose host language like Racket or Haskell works, right? Where there's some core language, there's an optimizing compiler for that core language, but then there's an extensible elaborator that takes us down to that core language. So instead of, as our core, implementing a compiler for this language, we're going to implement a compiler for sort of the lower level core language before we go down to Racket, but that has taken away any syntactic sugar from miniKanren. So that's the language we're going to start with. So let's see how we start doing that by writing, let's see, we want this window and this window. Great. So on the left, the language, program in the language that we want. And at the top of the file, this is all sitting inside Racket like a conventional macro system in that sense, where both our DSL programs are going to sit inside the host language, and the specification of our DSL is also going to sit inside of our host language. So at no point do we have to sort of jump out of the tool chain and run a make file or anything like that. So what we're going to do is we're going to write down a specification of that core language that we would like to macro expand to and then compile. So this sort of creates that intermediate point in that process. So we do that using the meta language called syntax-spec. And the essential, sort of most essential part of that is just writing down a grammar for the DSL. So we're going to have a couple of grammar non-terminals. We're going to have productions in those grammar non-terminals. So in miniKanren, the important things are we're going to have goals, succeed, fail, equality, that kind of thing. And we're going to have terms. So terms are going to be the expressions for constructing the values that we're going to work with. And you can see that sort of every sub-expression that we have, we indicate which non-terminal we're going to use to parse that sub-expression of each production. You can have ellipses and ellipses with pluses. So it's all, yeah, exactly, for relation arguments. And this is, of course, it's not extending grammar in the sense of matching strings. It's extending a tree grammar or matching S expressions. All right, so that's the first part. The second part is the connection to the host language. So if we just had a grammar of terms and goals, well, that's completely independent from Racket. So how do these things connect? How can we ever actually have terms and goals in the context of a Racket program? So this is where we define these host interface forms. And those are the boundary between the DSL and the host language. So defrel can appear in a Racket definition context. That's why we use host interface / definition. And run can appear in a Racket expression context. So we use host interface / expression. And they just sort of provide the production as though this was like another grammar non-terminal. So it's like a grammar production for that boundary. And then the other thing that we're providing here, the to-dos, are this is where we're going to invoke a compiler for the DSL eventually. But so far, we're not going to do that. And you can ignore the left-hand side and the right-hand side part for the moment. We'll get back to that later. So now that we've done this, now that we've written that specification, when you want mutual recursion, the things that mutually recur have to be in the same block. So I couldn't separate, well, terms don't contain goals. So in this case, I could have separated out each subform of the syntax-spec. I could put them all in one, too. Yeah. All right. So let's see what we get from having done that. Well, the program still does nothing. It prints to do. So in some sense, we got nothing, really. Until we think about what happens if I make a mistake. So this is something that you could plausibly try and do. What if I try and unify a logic variable with an equal equal. And if you did this in faster miniKanren, what would happen? Well, you would end up with a store, a substitution, that mapped Q to a procedure object that was the host language procedure used to implement the equal equal, right? Which is really not what you want. It doesn't make any sense. So by declaring a grammar, declaring that goals are separate things from Racket expressions, we can sort of catch these kinds of errors immediately, even in a language without types. So that's sort of the first thing. Here's one other kind of grammar error. What do we think this should do, given the grammar that we've written so far? Should this be loud? Should it be an error? Shouldn't be loud? Michael says it shouldn't be loud. Well, let me comment the first one. Okay, so we're asking about the second one, right? So unfortunately, yes, plus could be a relation, right? As far as we've specified so far. We just said it had to be an ID, right? So this sort of reveals that in order to get a complete sort of static specification, we're actually going to need to specify a little bit more. We're going to have to specify binding structure as well. And be able to distinguish things like Racket value definitions from relation definitions. So that's the next step. So let's take a look at the spec augmented to do that. So now inside the syntax-spec block, the first thing that we're going to define are these two different binding classes. And whenever we have a variable binding or a reference, we're going to assign it a binding class. And so if you were to refer to a name, say the binding had relation name as its binding class and the reference had term variable, that would be an error. So it'll catch that error for us statically. So the places where we use it, well, you can see that when we have a variable reference in a term, right, that's referring to a term variable and not a relation, right? You can see that now when we have a relation application syntax, that we specify that we want something that is actually a relation name there, not a Racket value, right? And then we have to think about bindings, right? So in fresh, we have a position which we say is a term variable, but this one's different, right? This one isn't a reference to a term variable. This is a binding of a term variable. Binding of a term variable, which is a sort of a static kind of variable binding to a logic variable value is what's happening in fresh, right? And so we need to specify that, yes, that's a binding, and where's it scoped, right? Of what? That's binding class. All right. So here is where we say, well, there's going to be a new scope, and there's so the thing that was x, that term variable, that's going to be a binding in that scope. And then the body of the fresh, the B, is going to be visible within that scope, so it'll be able to see the binding. And so if you think about scope as a tree or a scope graph, then you can sort of think of these binding rules as templates for a fragment of a scope graph that sort of gets put together. Let's see. So host interface forms also need binding rules. So the binding rule for run looks very much like the binding rule for fresh. We are binding the query variable to be in scope in the body of the query. And there's a part of the binding rule for relation definition that also looks very similar, where we're binding the relation arguments to be in scope in the relation body. But then there's this other piece. There's how do we do the binding for the relation name? So the relation name is a little bit different because the area that we want the relation name to be in scope for is the surrounding context of wherever the relation definition is, right? If it's in a Racket module, then we want the relation name to be visible throughout the Racket module. If it's in like a block, we want it to be visible there. So that's what this sort of export binding rule lets us say. And then the last change that I've made here, and this is just going to be sort of to illustrate something, is that now I have put in a compilation rule for each of these interface macros. But it's a trivial compilation rule. It's just going to quote the syntax and pretty print it so that we can see what it looks like. But we haven't actually compiled it yet. So let's see what we can do now that we've added those rules. So this is the version that refers to that spec. And the first thing sort of to notice is that we can hover over variables, and Dr. Racket understands that binding structure now, which it did not previously. That wouldn't have worked before. We should be able to run an example like that one that we tried before and see that it's an error. We get the complaint that plus is not bound as a relation name. Turns out that it's bound as another kind of thing. But and then sort of the last thing that I want to show you is, and this is why I wanted to print the syntax out. So right now, if we just sort of look at the last line here, what happens when we print, this is sort of the code that our DSL compiler is going to receive when that run gets expanded and compiled. And just the thing that I want you to notice is that in this program we had two x's, two bindings of x. And in the program that the compiler receives, those are distinguished. So there's one numbered x12 and one numbered x13, right? And we can see that the reference is known to refer to x13. So at this point, having the binding information has allowed syntax-spec to alpha rename the program for us so that we can be sure that our compiler is gonna sort of do the right thing without having to think quite so hard about scope. Now there are cases, Michael's probably thinking about it, right? If you write an inliner for your compiler, you duplicate syntax or something like that, right? You're still gonna have to do some work to make sure that there's hygiene in your compiler at that point, right? But this is a starting point. Okay, we can talk about that, but I think the point in this system is that we do have binding rules for all the core forms, and that's actually going to give us enough information to be able to do that. If you don't believe me, though, we should talk about it offline. Exactly, yeah. We've gone all the way down to the core language using those binding rules. Exactly. All right, so this is actually just for the demo. In the real system, there's a little flag that I turned on down here to show variable numbers, right? But the real representation here is, of course, a syntax object in Racket that has lots of different parts, including a source location and the original identifier, and enough scopes to make sure that these things are unique. So. All right, so that was the binding part. So the next thing is we'd like to have our nice syntax back. We wanted to write this syntax, not this nastier syntax, right? So let's get that back now. So here's how we add that to the syntax spec. So we had binding classes. Now we have extension classes. So extension classes are sort of categories of different kinds of macros. So we have term macros, we have goal macros. You can't use a term macro where a goal of macro is expected. You'll get a nice error if you try. And in the grammar, we then just say, well, where is each type of macro allowed? So fairly straightforward, I think. And this is sort of all we had to do to take our language that was not macro extensible and now make it macro extensible. So now we can define macros effectively using Racket's standard macro system on top of this DSL. So let's take a look at an example of such a macro, condi, for example. So condi expands to a disjunction with a sequence of conjunctions inside for each clause in the condi. And this is really just implemented with traditional syntax rules. You could use syntax parse or any of Racket's other pattern matching and templating languages. It's just a syntax to syntax transformer, the usual Racket sense. The only thing that's a little funny is we define it with define DSL syntax instead of define syntax. And that just lets us specify what kind of macro it is. So once we've defined a bunch of macros like that, I remember there's one more thing that I wanted to show you here. One more point that I wanted to make is that some of these macros that we define could be over things that have binding structure, right? So we define a version of run that accepts as many query variables as you want, right? And that desugars to a run with a fresh inside it that binds those query variables, right? And so we're desugaring to DSL syntax, right? And so we want to make sure that this is a hygienic macro expansion. And the other thing to note, though, is that for the core language, we had to write down binding rules, right? So when we defined the core fresh, we had to write down a binding rule. But when we write down the macro that expands down to it, just like when you write a macro that expands down to core Racket, you don't have to write a binding rule. So we figure that out through scheme-style macro hygiene that's been lifted to our DSL syntax. So let's take a look at what that lets us do. So here's the surface syntax program. It's now using that version of the syntax-spec. And if I run it, it's set up again to show the syntax that comes into the DSL compiler. And what we'll see is that the desugared version comes into the DSL compiler. And so this is sort of the important point in reconciling extensibility with optimizing compilation, is that you can have extensions, but by the time they get down to your DSL compiler, they'll have been desugared away. And so your compiler knows that it only has to deal with the core syntax that it's been designed for. All right. So this one's irrelevant. And OK. So the next step, obviously, is it would be nice if we had an actual implementation that compiled the syntax, right? I'm not going to go into the details of compilation, because it's sort of standard Racket stuff, but I'll just show you where it plugs in. So here, what I'm going to do is I'm going to require this compiler file, and that's just full of conventional Racket stuff for the moment. And then I'm going to invoke that in the host interface forms. So it's simplest to start with host interface forms that are expressions. So we're just going to end up invoking a sort of a conventional Racket macro called compile run. It could also just be a compile time function. You could have a compile time function that composes a bunch of other compile time functions for different passes, right? You could have a nanopass compiler. You could convert your syntax to the nanopass framework if you wanted. You can use whatever Racket you want for the backend compiler of these, is the point here. Right. So now it runs. And I also just used, there's a runtime system behind the compiler, and that's just the standard Reason Schemer second edition. So now that runs, but there's still like one other question of static semantics, right? So if I write this program where I call appendo with the wrong number of arguments, right? And this is sort of a static semantics aspect that is not captured in the grammar. So that means that right now what's going to happen is that I'm going to get a Racket error from the procedure call at runtime. And it's going to have a bogus line number on that, right? Because it's going to come from the place where I generated the procedure call at runtime. So this is not a nice and friendly error, which is what we've been trying to achieve. So we would like to be able to sort of add a bit more static semantics to catch this kind of error at the miniKanren level, right? So for that, I am going to dig just a little bit into the compiler to see how we can do that, because there's something interesting going on there. So here's one more version of the spec. This time, the thing that we're changing is that we have added in the interface macros, or the interface macro for defrel. So this is the interface macro for defrel. And now I'm going to explain what this left-hand side, right-hand side thing is, right? So when you have a definition context in Racket or any extensible language, it has to sort of compile in two passes. First, you have to find out what are all the names that are bound in this context before I can compile the right-hand sides that may need to refer to those names and may refer to names that are defined further down in the context. So that's why we have to take two passes, right? So if we want to record information about how many arguments a relation is meant to take, so that when we have a relation call, we can check that information, well, the place that we should record that information, when we should capture it, is while we are sort of taking that first pass along the left-hand sides of the definition context. So that's what's happening here. When we're compiling the left-hand side of a definition of a def-rel, we're going to do this effect of recording the relationarity. And let me, how fancy is Dr. Racket? Open defining file. Let me show you how that works. So the definition of that is a symbol table set bang. So it's really just mutating a hash table effectively. But it's a very special kind of hash table called a persistent symbol table. So the idea here is that if you think about like in a typed language, right, and the sort of the compiled files in a typed language like Haskell, right, they're going to have some low-level assembly that's implemented in all, right? But they also have to have a header that contains static information about all the bindings in that file so that when you load up another module that depends on it, you can type check that other module, right? And when we're talking about compilers, we're often talking about symbol tables. So a persistent symbol table is just a way of effectively adding information to that header that's stored together with the module so that we can record that this sort of symbol that we receive, rel name, has some associated static information with it, the arity. So it's sort of a reflective mechanism for doing that. And the important aspect of sort of storing it in the module header as opposed to it just being a compile time effect is that then when we have a program, so in this version of the program, I've defined appendo in one module, right? And now I make my arity mistake while trying to query it in another module. And imagine for a moment these modules are separately compiled, right? So I compile the first module, and I produce sort of Racket bytecode for it, and I shut down the Racket VM. And I start up the Racket VM and load it up for a dependency, and then make an arity error, right? We need that information that we recorded to be available when we sort of check the arity of the relation call, right? So it's important that the macro system provide this extensible way of recording static information about names. And this is one of the things that Racket's macro system lets you do that I haven't seen in template Haskell or MeadowCamel or anything like that, MacOCamel. So I think that's really important. All right. So we're sort of done with the basics. I'm not going to show you the optimizing backend itself. There's just a lot to it, but it's all conventional compiler stuff, right? There's nothing special about the macro system or the implementation strategy that's necessary to do that stuff. But what I do want to show you is the consequences of sort of mixing together the extensibility that we just saw here with those kinds of optimizations, right? Yeah. Oh, I didn't run it. There we go. Knows that it's talking about relations. It knows to highlight the right place now. Thank you. Sure. That's in compiler. So just when we get to the case of compiling goals where we compile a relation application that looks like this, we just see, well, syntactically, how many term arguments are there actually? And then look up in the table with a symbol table ref, how many did we expect, and raise an error if they're not the same. Other questions? Cool. All right. Okay. So now we can start doing fun things that combine these. So here's our appendo relation, but maybe we don't like being quite so verbose, and we'd really prefer that we had a pattern matching extension. So here's a pattern matching version of this using the matchy pattern matching extension to miniKanren, which is just a macro, and it's ideally that macro would desugar to something very much like what we wrote by hand, ideally, right? But let's see what it actually desugars to. Is it the ideal thing that we would have written by hand? So we can find that out by using this little tool where we can say print the relation code of appendo/m, that's the matchy version of appendo, and it'll show us what it expanded to. So Why did I get two versions? What did I do wrong here? Oh, I wanted this one still commented out. Alrighty. So here's the pattern matching version, and here is the code that it expands to. So I want to call out that there are some things here that are not in the other version, right? So the way the pattern matcher sort of desugars is it says, well, there's a list of arguments, right? There's a list of arguments to be matched on, right? And the simplest way to match is just to unify, right? So the simplest way to write the pattern matching extension is to shove all these arguments into a list and then unify each set of patterns with that same list. So here's the variable for the list, match_args. Here's where we shove L1, L2, and L3 into that list. And then in each disjunction branch, the first thing, the first conjunct of the branch, is going to be a unification that looks very much like the pattern, right, with that list. So here's the unification for the pattern in the second case, right? So now I'm going to scroll up, and we're going to take a look at Appendo, and we're going to see sort of what's different, right? So Appendo doesn't have this match_args thing at all, right? The handwritten version. And in the first branch, it directly unifies with L1, the empty list, and L2 and L3 together. And that's something that only happens indirectly here in the macro expansion, right? So unfortunately, that's going to be less efficient if that was the end of the story, because we're allocating extra variables, extra lists, putting more things in the substitution, doing more indirections in our unification solving. So maybe the story of extensibility isn't so good. But fortunately, we're in a language that has an optimizing compiler. And one of the things the optimizing compiler does is constant propagation and dead code elimination. So it will at least partially be able to fix this program back up for us. So that's what I'm going to print next, is the version of this relation after constant propagation and dead code elimination. And I'm going to sort of keep both versions on the screen here, assuming my screen is big enough. Make it a little smaller so that it does fit. So we can see that in the second version, there's no more match_args. Match_args has been removed, right? And this unification, match_args is gone. And now in the first disjunction clause, instead of a unification that goes indirectly connects via match_args to L1, L2, and L3, we directly have unifications with L1, L2, and L3. So what happened is that constant propagation saw that, okay, well, when I'm unifying with match_args, match_args is always the list L1, L2, L3. So let's just sort of inline that, right? And then simplify these unifications. And then after we've done all that, there's no more uses of match_args. And so it's dead code, and we can remove it. So you will notice, however, that there are some things like fresh nil, right, that aren't in the handwritten code that it would have been nice if we could have removed them. And sort of the problem here right now is that our goal with hosted-miniKanren was to have something that was a drop-in replacement for faster miniKanren. And in miniKanren, like, it's sort of not defined what answers come back, but it matters when you're writing the tests, right? For lots of applications. So if we do things like drop a fresh in faster miniKanren, that changes the search order, because that's one of the things where those inner leaves go in the search order. So that's kind of unfortunate that right now our constant propagation and our dead code elimination, because of that goal, is so constrained, right? But I intend to eventually add a mode to the compiler where you say, yeah, I don't care about the search order. Make it faster. Right? Though there's another problem that you can't, changing the search order in any way in miniKanren, if you're doing a run one query, say for program synthesis, right? Any perturbation on the search order could, in theory, make things worse, right? If you give me any miniKanren goal and transformation, I can provide you a context where that transformation makes it worse. So that's a consequence of the miniKanren search. Anyway, so that's the example with matchy. let's move on and see how extension interacts with being able to interact with the host language. So for that, I need to introduce a different program, different problem. The problem here is that we would like to be able to find out how many ways we can get from Seattle to Houston in some kind of airline network, where we have defined the direct flights here, just as a concrete set of pairs, right? And where we've then defined sort of a reflexive transitive closure of the direct relation using a recursive relation. The details of route kind of don't matter, so I'm going to hide that so you stop thinking about that. But this is the problem that we want to solve, right? But in the real world, there aren't only 6 flights operated by any airline. So really, for the direct relation, we don't want to hard code this, right? We want to talk to a web service or maybe download from a web service into a local database, something like that. And then we can use miniKanren to do what miniKanren's good at, defining the route relation on top of that. So by having a foreign interface, we can do that. So in this version of the code, the route relation is exactly the same as it was. What we're interested in is the definition of the direct relation, right? And in this case, what we want to do is we want to download, say, a CSV of flights data from a web service somewhere. And then we want to store it, say, in SQLite in a database. And then, because there could be thousands upon thousands of rows, we want to sort of query efficiently into that database. So create flights table is going to return a database connection of some sort. And then we want to be able to write the direct flight relation by doing a database query. So to do that, we have to sort of escape out of miniKanren and into Racket. And in this sort of multi-language style, we have to do that explicitly. So in faster miniKanren, say, you can just put Racket in the middle of something. As long as you implement the right interface, you know how to do the lambda state thing. But here we're going to have to be explicit about it. So we're going to say goal from expression because we're in a context where we need a goal, but we would like to write a Racket expression to provide it. So this name is sort of inspired by Matthews Findler multi-language semantics and the way they structure multi-language semantics. So in this particular case, what we want to do is we want to do our database query. It's going to take our connection, and then it's going to take the values that are known about the logic variables A and B. Now, they might be logic variables, and our query has to know how to deal with the fact that, okay, maybe there's a value that we can't use as a filter, as a where clause in our select, right? So query flight rows has to be a little bit intelligent there. But we want to give it sort of whatever value we do know. And so that's where we have to sort of take a miniKanren term and obtain a Racket value that has as much information as is currently available. So if you know a miniKanren implementation, we walk it in the store to find the current value. But one more thing we want to do is we want to make sure that this interaction doesn't sort of create some problem by which the Racket code can observe optimizations that might have happened, or can do something with the runtime data that would make the compiler's understanding of the semantics incorrect. So an example of this is that conventionally in faster miniKanren, a logic variable is just a vector, and sometimes that vector has a mutable cell in it to sort of keep an optimized version of the current value of the logic variable, right? And so if we just expose that vector to Racket, then this code could access a logic variable and mutate it, right? And we could do something that would totally break the semantics of miniKanren and mean that our compiler its optimizations are unsound now, right? So instead, when we say expression from term and a value crosses this boundary from miniKanren to Racket, what we're going to do is, if it's things like cons, pairs, or numbers, and the values are known, those translate to Racket cons, pairs, and numbers. Those are fine. But for logic variables, we're going to wrap them in an opaque structure that you can't look inside and you can't manipulate. And then when they go out the other end, when we go from Racket back into miniKanren, we're going to unwrap those opaque structures again. And the reason why we do that in the first place, instead of just always having an opaque structure around everything, right, is that we want to avoid having to have values in miniKanren, in the miniKanren runtime, be wrapped, because that would make things slower, right? So we want to be able to have those sort of unwrapped representations when we know we're doing safe things, but wrap them up when we cross the boundary into miniKanren. So that's what having the explicit boundaries is going to let us do. However, it turns out that we can infer when we need to write an expression from term. So I don't actually have to write expression from term A. I can just write A, but understand that because we're in a situation where A was bound as a term variable over here, and we're referring to it as a Racket variable, the macro system is going to do something special for us, and it's going to say, okay, I'm going to wrap it in an expression from term for you, and we'll get that boundary protection behavior that we want. All right, so we write our query, we get some rows. Oh, yeah. I don't know, I'm sorry. Ask Robbie. It might be because I'm collapsing some S expressions and it breaks. All right, so we run our query, we're in Racket code, we have some rows, right? And these rows are all going to be totally concrete values, right? Of ground data that came back from a SQL-like query now, right? And as far as we could tell from what we could see about the variables, they're all compatible with the variables A, B, right? Now, it may be that they're not actually compatible because the variable A has a disequality constraint on it, right? That we didn't know about and we couldn't take into account when we did the database query. So ultimately, what we have to do is, in order to sort of finish this, we have to construct a goal that's going to unify each one of these rows with the variables A and B. And that unification is going to do the work of checking that all the constraints that we may not have taken account of so far hold. And so the way we're going to do that is we're going to say, okay, well, we're in an expression context, but we need a goal. And so to produce a goal, we're going to use expression from goal, which takes us back into miniKanren land. And the goal that we're going to use, Mitch and I figured this out last night, the clean way of doing it. The goal we're going to use is a call to the member-o relation. So we say sort of the row with the logic variables that we weren't sure of, right? That one should be a member. It should be one of the rows that came from the database query. And the member-o relations evaluation will do the sort of non-determinism for us to branch and end up returning the right number of times with valid rows. So definition of member-o is here. It's just a totally standard miniKanren relation. And I believe all this should run. I'm not connected to the internet, so it doesn't run. I'm sorry. I could be connected to the internet. Well, no, yeah. It's public Wi-Fi. We'll see if it connects and I can get my flight CSV. All right, there we go. So my query was, give me 10 routes from Seattle to Boston. And here are 10 routes. Real data. Yeah, miniKanren with real data. It's not too often that you see it talk about that. All right, so this was nice, but you gotta think hard, right? You gotta scratch your head and figure out where to put the expression from term and term from expression and goal from expression. And multi-language programming is just fundamentally a little bit tricky. It's not too hard. But wouldn't it be nice if instead we just had a part of miniKanren that knew how to talk to a database, right? Shouldn't I, as the hosted-miniKanren author, have created a facts table part of miniKanren where you can define a flights relation with sort of these two arguments and have it be defined by some data that you load from the internet, right? And then we could just query it like this. This is obviously a nicer programming model for database access. And the nice thing is that we can just implement query facts as a macro on top of all of that multi-language interaction that we did. So from the user's perspective, you can't tell that it's interacting with Racket. is very careful to make sure that, for example, if I tried to use, well, let's find out, but I'm going to tell you that if I tried to do something wrong, like use Racket here, plus 1b, even though this is an extension and it's using Racket under the hood, because we put the boundaries in the right place, I hope I did, we'll still get an error telling us that we expected a miniKanren term in that position. And that's because the expansion of the query facts macro used expression from term to wrap the thing it got in, to say this is going to be a term and I'm going to translate it in. So I think that's really cool about the interaction between extensions and this multi-language structured host interaction. All right, and it looks like I have 10 minutes left, so I have time. Last night when I practiced this, we did not get there. But let's look at how our optimizations interact with the host language interaction. So this is an optimization that I believe Mitch did most of the work for, which is to do a little abstract interpretation to figure out when we don't need the occurs check. So in this particular relation, if we look at the unifications of A, so unification of A with list 1x, right? Well, if we didn't know what happened between the fresh and the unification, there could be a cycle, but we know that there's nothing after the freshing of x before the unification with A. So we know that x cannot contain A, right? And so this is a case where we don't need the occurs check, right? And the other thing is just a constant, right? So we can omit the occurs check here. We can also omit the occurs check from the second unification, because again, we know that y is fresh, right? But then when we get down, if we wanted to unify x and y, right? Well, if we hadn't had the previous two unifications, that wouldn't need it either. But it could be that, that A and B have some related parts, right? They came from the outside world. So as far as an abstract interpretation, we don't know anything about those things. They're top, right? And so that means that when we do this unification of x and y, we are going to have the occurs check in order to make sure that there are no cycles in that term at runtime. So we have an analysis that does that, and we can sort of see the output of that analysis. Unifications marked with not needing the occurs check. And then we can just generate code, a version of unification that doesn't have the occurs check. And sort of the interesting interaction that I want to point out here is what happens when we have some unknown Racket code in the middle of the program that we're trying to analyze. So here we have R2, and from the first unification, we know that x is a ground value, right? Finite ground value can't possibly have any cycles through other variables. But then we have some Racket code that does who knows what, right? And then we have a unification of A and B. They were originally fresh, right? Before the Racket code that does who knows what, right? And then finally, we have a unification of x and y. So the question is, which of these unifications is it safe to omit an occurs check for, assuming that we can't analyze the Racket code that sits in the body of this goal from expression, right? And what is safe to do here really depends on how we've designed the foreign interface, right? So if the foreign interface was something that could access all of the miniKanren runtime state, right? Access the substitution and return a modified substitution in whatever way it wanted, right? Well, then we couldn't be sure whether these things could be cyclic terms afterwards. Anything, all bets would be off after that Racket goal from expression. But in fact, what is possible in goal from expression, the only way that goal from expression can return is by producing a miniKanren goal using expression from goal. All we can do is use miniKanren goal constructors, and there's no way to access the underlying runtime. So what we know is that whatever goal does get returned from here is going to have miniKanren semantics, right? And so we know, for example, that it's going to update the store monotonically. So we know that x, because x was fully ground to the cons pair 5 and 6, that after this, x must still be fully ground to the cons pair 5 and 6, because our foreign interface didn't provide us any way to break miniKanren semantics. Now, on the other hand, A and B are in scope for that goal from expression, right? It can see A and B. And so in the body, we might have a unification that somehow relates A and B, right? And so that means that we can't assume that A and B are disjoint anymore afterwards. We have to be conservative in our analysis. So the consequence of this is that when we run our analysis, we say, okay, there's definitely no occurs check needed for x and y, right? But there is still an occurs check needed for B and A, because those are things that could have gotten related to each other inside the goal from expression using sort of legitimate miniKanren code that we can't observe as the compiler here. Anyway, so that's the way that our sort of boundary design, these explicit boundaries, these limitations, mean that we are able to have multi-language interaction while also having a sound compiler. So we have optimizations. Sometimes they make things faster. The only one that really works is removing the occurs check. That works quite well, right? Changes the complexity class of an algorithm. The other ones, they only help a little bit. And so sort of the takeaway is that by writing down this explicit specification of our language, we got a lot of stuff for free. We got syntax checking, IDE services, hygienic macro expansion, static checking that works with the separate compilation, and we were able to implement these boundaries that protect the interaction so that we can have an optimizing compiler. Try it out. Add some optimizations. We'd love to have some contributors, and we also have an ICFP paper. So happy to take questions.
I just have a simple question. In all of the examples you showed, you had a random order of terms in a unification. For example, in the last one, you had B and A unified, whereas the original code unified A with B and stuff like that. Is it random, or is it like caused by something?
So when we generate code, we're always generating unifications with a variable on the left, and then the ordering of the variables, I think, depends on sort of the order in which they were bound. So there's just sort of a total order on the variables, and yeah. No, I know what you're talking about. I know exactly what you're talking about. But it may have been that we built the list right to left on the fresh bindings or something like that, right? Yeah.
And the runtime will associate the...
Yeah, the runtime also orders unifications according to variable age as well. So yeah, the order kind of doesn't matter mostly.
Can you say a little bit more about the abstract interpretation? Like what? So you showed an example of it, but is there any more than like kind of what you showed, and what's the general approach? What do the abstract domains kind of look like? That sort of thing, to whatever degree you want to say.
All right, I mean, I didn't do like when I implemented that pass, I didn't do like a lot of, it's not backed by a lot of theory. So if you want like the theoretical backing, Michael would be the best person to answer. It's very straightforward. It's like, I don't know, 50 lines of code because the number of forms is very small. It's basically like, you know, if you can prove it's a ground, then you can always eliminate the occurs check. If it's fresh, then there's a lot more risks. And if things are coming from some unknown place, like a relation call, or are arguments to a relation, then they're just basically immediately top. That's good. Yeah.
Anything else?
So thank you so much.